All right, but let's start with some trigonometric integrals. Let's look at a problem that came up in your homework in a couple spots, and that's to integrate sine squared. Integrate sine squared theta d theta. There's two ways this can be done, and that was supposed to be the point of a couple homework problems. One way is to use integration by parts. Let u equal sine theta and v prime also be sine theta. Then the product of those two functions is the function you're trying to integrate. And it's relatively easy to find u prime and v. U prime is the derivative of sine, which is cosine. And v is the integral of v prime, which is negative cosine. As I've taught you, it's typically a good idea to write down the integration by parts formula every time you need to use it to get it sinking into your brain deeply. That'll benefit you for the gateway exam. U times v minus the integral of v times u prime with respect to x. Some books call this dv instead of v prime. They write dv would be sine theta d theta. Well, actually, in this case, the variable is theta, so I should use a d theta here. That's supposed to be a theta. And you'd see the formula as u times v minus the integral of v du is another way you'll see it written. But go ahead and use that here. So you always end up multiplying the functions that are in the upper left to lower right here. That's u times v. So that'll be negative sine theta cos theta minus the integral of the product of these two things on the bottom. Notice there's already a minus sign there. So the two minus signs make a plus sign. We get plus the integral of cos squared theta. This should feel a little familiar. You could use integration by parts again, use it twice. Let u equal cos theta and v prime be cos theta, and that would be a fine way to do it. But it's actually not necessary at this point because we have trigonometric identities. You know that cos squared theta plus sine squared theta always equals 1. Therefore, cos squared theta is 1 minus sine squared theta. And you can go ahead and make that replacement. Those are equal no matter what theta is. So we get negative sine theta cos theta plus the integral of 1 d theta minus the integral of sine squared theta d theta. This is just a theta right there. Now look at what we've got. We've got the integral we want to know on the left side equal to all this on the right side, including the integral we want to know. So we better try to get that to the other side. We better add the integral of sine squared theta d theta to both sides to cancel it on the right and get 2 times the integral we want on the left equals negative sine theta cos theta plus theta plus c. It'd be okay to call it c here and then divide by 2 and still call it c. Maybe for conceptual clarity, I'll just call it c1 to start with. And then after I divide both sides by 2, then I'll call it c. So the final answer is the integral of sine squared theta is negative 1/2. I'm dividing by 2. Sine theta cos theta plus 1/2 theta plus c, where c really is c1 divided by 2. But you don't have to mention that. You can just circle it as is. The other way to do this integral is a little quicker, but you've got to remember something, and that's a trigonometric identity. It's worth remembering this. It's worth remembering this trigonometric identity. Integrals involving powers of cosines and sines do come up a fair amount in applications, though mostly those applications are in multivariable calculus, calculus 3. something called polar coordinates and spherical coordinates with double and triple integrals, which sounds kind of scary. Those kinds of applications are where you often have to integrate these kinds of functions. I remember it. Sine squared theta is, it turns out, 1/2 minus 1/2 cos 2 theta, not sine 2 theta. That's related to a certain double angle formula for the cosine function. That's where this comes from. The double angle formula I'm thinking of, double angle formula, says that cos 2 theta is, see, I think it's, I can just solve this for cos 2 theta. It's, say that again?
Isn't it 2 sine theta?
That's a double angle formula for sine 2 theta instead of cos 2 theta. Should be 1 minus 2 sine squared theta. You can check it by graphing these functions that they're the same. You can also just plug in a few numbers to double check it. If you plug in, for example, theta equals 0, cos of 0 is 1, sine of 0 is 0, you get 1 minus 2 times 0 squared is 1. On both sides, you get a 1. If you, for example, plugged in theta as pi over 4, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0, excuse me. If theta is pi over 4, so that 2 theta is pi over 2, cos 2 theta is 0, and 1 minus 2 sine squared theta, which is pi over 4, is 1 minus 2 times the sine of pi over 4 is 1 divided by square root of 2. I got to square that. I still get 0 in the end. That's not a proof, right? That's just checking a couple numbers, but it does work. And this integral is easy to do. Integrate 1/2, get 1/2 theta. Integrate 1/2 cos 2 theta. If you can't just do it in your head, you could use a substitution, W equals 2 theta. But I'm hoping you're getting to the point where you can do this in your head by guessing to get minus 1/4 sine 2 theta plus C. And this is where the trig identity that David was thinking in comes into play. Sine 2 theta is the same as 2 sine theta cos theta. And that's why these two answers here and here are actually the same. They look different, but they're really the same. It's because sine 2 theta equals that. 2 times 1/4 is 1/2. Negative 1/2 right there matches what you get there. And we still have the 1/2 theta as well. Okay. Either form of the answer is okay. To tell you the truth, I prefer this way because I just remember the identity. There's a similar identity that can be used to integrate cos squared theta. And remember that sine squared theta plus cos squared theta always equals 1. What can I put inside the parentheses here so that if I add it to this, I always get 1? It would have to be 1/2 plus 1/2 cos 2 theta. If you add those two things, the terms involving the cos 2 theta cancel. And 1/2 plus 1/2 is 1. It would have to be this. Kind of strange. This one involves cos 2 theta, so does this one involve cos 2 theta. Strange but true. This is also related to a double angle formula. It's related to the fact that cos2 theta can also be written as 2 cos squared theta minus 1. It's another double angle formula. This, by the way, is another double angle formula that sine2 theta is 2 sine theta cos theta. Strange that the double angle formulas for sine and cosine are so different seeming, but it is true. And now this one finishes to be 1/2 theta plus 1/4 sine2 theta plus c, which again could be rewritten using the fact that this is 2 sine theta cos theta. So if you're going to rewrite it based on just sine of theta and cos theta, the answer would be 1/2 theta plus 1/2 sine theta cos theta plus c. But either way you leave, the answer is okay. I guess the second way is going to be simpler for certain applications, including one I show you here in a few minutes. These integrals are important and show up on homework and should show up on regular exams. They actually do not show up on the gateway, but they could show up on homework and regular exams. The next integral I'm about to show you does show up on the gateway. In fact, every version of the gateway has something like what I'm about to show you. So make sure you work at this kind. Products of powers of cosine and sine, where at least one of the powers is odd. And the example I'm going to pick is integrate cosine of x to the 6th times sine of x to the 3rd. To make this integral relatively easy, at least one of those powers needs to be odd. If they were both even, like if that were a cos to the 6th and that were a sine to the 4th, it becomes a lot harder. In fact, I can do this integral, if I'm going as fast as I can, in probably about 1 minute, maybe 30 seconds if I really, really rushed it. Whereas if I made that a sine to the 4th instead of a sine cubed, I'm guessing it would take me at least 10 minutes, maybe 15. Even going like as fast as I could. I haven't timed myself, so I don't know for sure. It's that much harder though. It's at least like 5 to 10 times harder if I made that a 4 instead of a 3. If I made it a 5, it's back to easier again. At least one of the powers needs to be odd to make it easier. Here's the method. Whichever one has the odd power, in this case it's the sine, peel off one factor of, in this case, sine, and put it next to the dx by itself. So I'm going to think of sine cubed of x dx as sine squared x times sine x dx. Why? Why do I want to do that? Because if I let w now be cosine of x, this will be w to the 6th, and this sine x dx will be negative dw, and that's good. What do we do with that? Use a trig identity. Replace it with 1 minus cos squared theta. Yeah, now let w be cos x so that dw is negative sine x dx, and make your replacements. Replace cosine with w to get w to the 6th. Do it here as well to get, in parentheses, 1 minus w squared, and replace sine x dx with negative dw. And that's a relatively easy integral to do. I'm going to distribute the minus sign through the parentheses here, though I could also put it in front of the integral and rewrite 1 minus w squared times -1 as w squared minus 1. Then distribute the w to the 6th through the parentheses to get w to the 8th minus w to the 6th. That integral is easy to do, to get 1/9 w to the 9th minus 1/7 w to the 7th plus c. Now you're almost done. Replace w with cosine of x. 1/9 cos x to the 9th minus 1/7 cos x to the 7th. There's your answer. What happens is if both powers are even, is you end up having to use these identities like multiple times. And it can be a real big pain. I'm sure, again, it would take me like 10 to 15 minutes at least. But when one power is odd, then you do this. If it had been the cosine that had an odd power, for example, if it was integral of cosine cubed times sine to the 6th, you'd put the cosine, one factor of cosine next to the dx, and you'd have cos squared times sine to the 6th times cos x dx, and you'd let w equal sine x. Because I put the sine x next to the dx, that's why I let w be cos x. So dw is almost there, up to a negative sign. I really should have put my dx here, by the way. Yeah, I forget to do it sometimes too. But it really should be there. What about if they're both odd? Then either the cosine or the sine can be put next to the dx. And then just let w be the other thing. I would probably tend to put the cosine next to the dx and let w be sine x. Just so I don't have to worry about the minus sign. These kinds of problems show up on every version of the Gateway exam. The Gateway exam is a common departmental exam, and so I don't write the problems. Mm-hmm.
So if you're always peeling off just one factor,
Mm-hmm.
from the odd complex.
Yep.
Okay.
Yep. But you do need to use an identity like this here as well. Mm-hmm.
So two things. First, so if say we've done cosine to the 7th x minus sine squared of x, we just do 1 minus sine squared cubed.
If this has been cosine to the 7th,
Yeah, you peel one off, so it'd be cosine so that you'd be doing the distribution cosine to the 6th, and would you do like 1 minus sine squared cubed?
you'd only do a 1 minus, okay, maybe this is related to it. You'd only do a 1 minus cosine squared cubed here, for example, in this kind of problem, if this were sine to the 6th right there, and say sine to the 7th to start with. If we had a sine to the 7th of x to start with, put one of those signs next to the dx, and you have sine to the 6th right there, which would be the same as 1 minus cos squared x quantity cubed.
Okay, so you always do that to the one that you subtract the one power off. On the other one.
Yeah, because it's based on what you let w be. Yeah.
And what happens if they're both?
Then you can do it either way. Put either one next to the dx. The final answers would look different because you do a different substitution, but they'd be equivalent.
Just thought that might.
Mm-hmm.
That might come up, so.
Yep. Okay.